Hello everyone, welcome to another lecture as part of our ME 6151 Computational Heat and Fluid Flow course. Okay, so in the last lecture we looked at overall simple algorithm on a staggered mesh, and we also considered the effect of under relaxation for pressure and the momentum equations, and finally we looked at the velocity and the pressure boundary conditions when solving any problem using simple, right? So in today's lecture we're going to solve essentially formulate three problems from Patankar's book, okay, in chapter 6, that is the fluid flow equation. So we look at the each of these problems and formulate them using simple algorithm. So the first problem we will look at is the problem 6.4 that is shown here. Basically this is a one-dimensional flow through a porous medium, and the black circles here indicate essentially the locations where the pressure is stored, and the red arrows here in the x direction denote the A, B, C denote the staggered locations of the velocity vectors, okay, denoted by A, B, C, okay. Alright, I have kind of also shown the corresponding control volumes. Of course, these extents in the y direction do not make sense because this is a 1D problem, okay. So essentially the area vectors are all 1, okay. But you can see that there is one control volume. This is basically for control volume for B, and this dashed line, this would be control volume for C, and this black one, this is slightly taller, is basically the one control volume for cell 2, that is the primary control volume for the pressure cell. Okay, so the governing equations are given as C mod u plus dp dx equals 0 and d by dx of ua equals 0. Okay, so essentially this equation is basically your what equation is this? This is your continuity equation. Okay, and what about this guy? This is the momentum or the x momentum equation. Okay, so all right, now what about this is the pressure gradient term. Area is the cross-sectional area that is basically given at what will be the effective area at different locations. So AB is 5 units, AC is 4 units, and also where C is basically the porosity constant, that is basically given. CB equals 0.25, CC equals 0.2, P1 and P3 are given. So basically these two pressures, that means we are given a pressure boundary condition. P1 is 200, P3 is 38, that is given, and we were also asked to take initial guess as for the velocities as UB star, UC star as 15, and the pressure for the cell 2 as 120. Okay, so essentially this is given, and then you are asked to calculate, use simple algorithm and calculate what is the final pressure P2 and the velocities UB and UC. Okay, the grid values, that is basically the delta x between 2 and 1 is equals 2, and so delta x for 2, 3 cell is also equal to 2. Okay, so basically this is a uniform this is basically a uniform mesh. Okay, all right, so what about the momentum equation? So this is the pressure gradient term. What kind of a term do you call this guy as? C mod u. What kind of a term would this be? Would this be convection? Would this be a convection term? No, it's not a convection term, because if this is a convection term, it's not just that you should have you should also have a nabla operator, right? You should have some del dot operating on this thing, which is not available. So this is not a convection. This is of course not unsteady term. This is also, is this a diffusion term? No, this is not a diffusion term. There is no nabla operator here. Then what kind of a term this would be? This would be essentially the only thing remaining is your source term. So this would be a source term. Okay, and is it linear or non-linear, the source term? Source term is non-linear because you have mod u times u, so this is a non-linear term. Okay, so we will see how to categorize this particular thing in the formulation. Okay, then let's get started. So if you remember the simple algorithm, what we do is basically write the momentum equations for the velocity control volume. So that means we have to discretize the momentum equation, that is basically this guy at B and at C. Then we essentially write an equation for velocity corrections in terms of pressure corrections from these momentum equations. for the staggered control volumes B and C. Then we write the continuity equation, that is for cell 2, that is for the primary cell or for the main cell, right, the pressure cell. Then using the continuity equation, we substitute for the flow rates from in terms of the flow stars and the flow primes, and then we substitute for the flow primes, the velocity primes in terms of the pressure primes, right, and then derive a pressure correction equation. Then we solve for the pressure correction equation and eventually correct the velocities and pressures and kind of keep iterating until the obtained values satisfy both the continuity and the momentum equations. Okay, all right, then let's get started with discretizing the momentum equation on the cells B and C. Okay, and thereafter we will look at discretizing the continuity equation on cell 2. Okay, fine. So the momentum equation is basically C mod u plus dp dx equals 0. So if we discretize on cell B has faces as cell B has faces 1 and 2. Okay, that means the integration has to go from 1 to 2. We have C mod u dx plus integral 1 to 2 dp dx equals 0. dp dx equals 0. This is basically integration on the finite volume. Okay, so we know that this is a pressure gradient term, and we just categorize this as a source term, right? And we know that we can write the source as SC plus SP Vp. So if you consider U as UP, means U2, then this is basically comes as your SP, right? Basically SC equals 0 and SP equals C mod U, right? And SP of course also needs to be evaluated at the cell centroid. So the cell centroid for this particular 1 to 2 is basically B, right? Essentially everything has to be evaluated B, and UP would be equal to UB, right? And SC equal to 0. All right, so we know that this is basically a source term. Then if you write this in terms of the SP Vp and then SVP, Vp would be evaluated the cell centroid, and that would be a constant. So constant times integral dx would give you x, and you have x2 minus x1. So that means essentially what you have is CB mod UB times x2 minus x1, right? That's what we have. That is basically integration of this particular first term, and the second term would be dp dx dx. Integration would be dp, right? Integration of dp would be p, that would be minus p2 minus p1 is what you get here. Okay, so for cell B, now we pretty much have the discrete momentum equation. That means CB mod UB times x2 minus x1. So if I write whatever is being multiplied with UB, that is CB mod UB delta x as a coefficient AB, then the equation we have is AB times UB plus P2 minus P1 equals 0, right? That means this is the discrete momentum equation for cell B, right? AB UB equals P1 minus P2. Now AB here is the coefficient. It's more like your AP term, right? So if you compare with your original equation, if you remember, we wrote A east U east equals sigma n B on B plus delta y times PP minus PE plus BE, right? So in this particular case, if you compare, you don't have BE, you don't have contribution coming from sigma n B here, because otherwise you should have got a term which is like UC times something that is not there. So only the central coefficient, that is A east U east, is basically AB UB. Now AB is basically the coefficient for UB. Okay, all right, so that is the discrete equation for cell B. Now if you move on, we will do a similar thing, integration of the momentum equation for cell C, that is basically for this cell centroid. So the limits of integration would be for faces, that is 2 to 3. Okay, and then integrate in a similar way and obtain, essentially for cell 3 we have west face is 2, east face is 3, so we have to go from 2 to 3, C mod u dx plus integral 2 to 3 dp dx dx. Then again this is basically your SC plus SP Vp, so this would come out to be CC mod UC delta x times UC plus dp dx dx. Integration would be pressure, that means applying the limits we have P3 minus P2 and equals 0. Okay, and this coefficient whatever is multiplying UC, if you take it as a constant, that is basically the coefficient, because we have to linearize the system, right? This is what is the linearized source term, and SP is known while we are doing the inner calculations, right? So that's why CC mod UC delta x would be the constant if we call it as AC. What we have is basically AC UC equals P2 minus P3. So this is the discrete momentum equation for cell C. Okay, so we have both the momentum equations. So if you were to write in terms of the star quantities, essentially we just have to apply for a given pressure guess and a velocity guess, what would be your velocities that you converge to. So in this particular case, we don't have a system to solve, because what we have is UB star expressed as pressure star. So the moment you have a guess value for pressure, you can calculate what is the value for converged value for UB star. Okay. All right. So that means your star momentum equations are AB UB star equals P1 star minus P2 star. That is basically, let's call it as equation 3. Then AC UC star equals P2 star minus P3 star. Okay. So this is basically the star momentum equation for the cell C. Okay. Now what do we have to do? We have to subtract the star momentum equations from the original equation, right? That means we take equation 1 and subtract equation 3. Similarly, we take equation 2 and subtract equation 4. That means what we get is, we get AB UB minus AB UB star, which will basically give you AB times UB minus UB star. That is basically your UB prime. So the equation we get is AB UB prime equals, similarly on the right hand side, the non-star values and the star values subtract off, leading to the prime values. That will be P1 prime minus P2 prime. And similarly, we have another equation, that is AC UC prime equals P2 prime minus P3 prime. Okay. So these are the velocity corrections expressed in terms of pressure corrections. Now what you see here is that this is we don't have to apply the simple approximation here, right, which was neglecting the contribution of A and B primes and U and B primes here, A and B and B prime, A and B and B prime, because those are already 0 here. So as a result, the simple algorithm need not be, the simple algorithm approximation need not be directly applied here, because the equations that we obtained already satisfy this condition, that the neighboring contribution is already 0, okay, to the velocity corrections. All right. But we were given what is the pressure at the locations 1 and 3. So P1 equals 200 and P3 equals 38. This is what is already given. That means because the pressure is given, what will be the pressure corrections at these locations? They should be 0. That's why that means P1 prime equals 0 and P3 prime equals 0. All right. So those are 0. That means if we substitute here, P1 prime is 0 and P3 prime is 0. So the equation we get is AB UB prime equals minus P2 prime. Then we can write UB prime as minus P2 prime by AB. Similarly, AC UC prime equals P2 prime, right? Because minus P3 prime is 0. Then UC prime equals P2 prime upon AC. Okay. So these are basically your velocity corrections in terms of pressure corrections, right? Essentially, we just have only 3 cells, 2 velocity cells, B and C, and 1 pressure cell, that is P2. We just have to calculate what is the converged values for UB, UC and P2. Okay. All right. Now we are done with essentially discretizing the momentum equations. So we will go and look at discretizing the continuity equation on the primary cell, on the cell for pressure, that is basically cell 2. Okay. So if you look at cell 2, the phases that we have are B is there on the left hand side and C is there on the right hand side. So that means if you go back, so we have for pressure cell 2, that is this black cell, we have the phases are B to C. Okay. So essentially we will integrate the continuity equation for B to C, and the continuity equation is given as d by dx of UA of dx equals 0. Okay. So that's what is given. That means if you integrate this, you're going to get UA, and if you substitute the phase values, what you get is UCAC minus UBAB equals 0. So this is your discrete continuity equation for pressure cell 2. Okay. All right. Now we know that, of course, because these are the corrected values as such, UC and UB, that if we represent them, then these are equal to 0. But if these were starred values, UC star and UB star, they would not satisfy the continuity equation. Right? As a result, we can, of course, now decompose this UC into star and prime, similarly UB into star and prime. Then what you get is UC star plus UC prime times AC minus UB star plus UB prime times AB equals 0. Right? So that means we have decomposed this into star and prime values. Then we can send the star values to the right hand side because those are known at this particular time, right? Essentially we can send UB star and UC star times AC and UB star times AB to the right hand side. So what you get is, you get minus UB star AB going to the right hand side makes it UB star AB, and you have plus UC star AC becomes minus UC star AC on the right hand side. So this is basically what is already known after the momentum equations are converged, right? Okay. All right. That means what you are left with is you are left with UC prime AC minus UB prime AB equals such and such on the right hand side. Now what do we do? Essentially we substitute for the velocity corrections, right? We substitute for the velocity corrections in terms of pressure corrections, right? From the equations we have derived. So that means substitute for UC prime in terms of pressure correction, that is basically UC prime equals P2 prime by AC. Similarly, UB prime equals minus P2 prime by AB. So substitute for these two. That means plug in these two into this equation. So what we get is P2 prime times AC by little AC. So capital AC is the cross sectional area that is given. Little AC is the coefficient of UC, right, in the momentum equation. Similarly, you get a UB prime has got a minus. UB prime has got a minus P2 prime by AB. As a result, this becomes plus. So what you get is P2 prime times AB upon AB equals, on the right hand side as usual we have UB star AB minus UC star AC. Okay. So essentially we got an equation here. This is basically P2 prime times AC by AC plus AB by AB equals UB star AB minus UC star AC. Okay, so we can rewrite this. Basically this is now your pressure correction equation in terms of the right hand side B, right, the star values and the coefficients. Okay, so this is your pressure correction equation. Now in this particular case, because we have only one cell, we don't have to solve a Gauss Seidel, right? But in general this would be similar to APPP prime equals sigma NBP NB prime plus B. Okay, so you should be able to make these comparisons at any stage. But once we calculate what is the right hand side value here, we can calculate what is P2 prime. That means we will know what is the pressure correction. So once you know the pressure correction, you can substitute into the velocity corrections, calculate the velocity corrections, then pressure and velocity can be corrected and the algorithm is complete. You can go back and to the step, the previous step where we have guessed the velocity and pressure and then flow down from there again, right? Okay. That means once you know the pressure correction and velocity correction, you can correct the pressure, that is P2 equals P2 star plus P2 prime. Similarly, velocities are UB equals UB star plus UB prime, where UB star is the converged value from the momentum equation and UB prime equals in terms of pressure corrections, that is minus P2 prime by AB, and UC equals UC star plus UC prime, that is UC star plus UC prime equals P2 prime by AC. Okay, so we now got UB, UC and P2. These UB and UC of course now satisfy continuity equation, but they do not satisfy the original momentum equation because the momentum equation itself is non-linear, right? We have C mod UU, where C mod U itself was taken as UAB. AB contains UB star values, right, which are now got updated, so they don't satisfy the momentum equations, the velocities. So because of the non-linearity, of course, they don't satisfy, and we also have to under-relax the equations because of the non-linearity in the source term. Okay, so let us under-relax the pressure. That means whatever is the P2 prime you got, you only multiply that with some alpha P and add it to the star value to obtain the original value. So P2 equals P2 star plus alpha P times P2 prime, and of course we know that we will not so basically do not under-relax velocity in this way, right? Because if you do it this way, because then it will not satisfy the continuity equation. So we go back and use in the context of momentum equations itself, whenever we are trying to solve it, we have to under-relax and use the under-relaxed equations. Okay. That means our original equation for cell B is AB UB star equals P1 star minus P2 star. So if you underlaps this equation, basically this is your AP value, right? This is like AP VP, right? That means you get AB by alpha U times UB star equals P1 star minus P2 star plus, for this contribution you would have 1 minus alpha U by alpha U times AB UB. I have used star star here basically to indicate that this is the previous iteration value or the latest value that we have, that we can use here. Okay, essentially to make sure that this is different from what we have here. Okay, so you would use this momentum equation when you solve for the cell B, okay, because this is the underlaxed equation and you can take some value for alpha U as 0.8 or something, and this underlaxation is necessary because of the nonlinearity in the source term. Okay, that means you will use this equation instead of the equation we have written here. Okay, when you try to solve, so when you try to solve the star momentum equations, instead of 3 and 4 you would use the underlaxed equation. Okay, now that means if you look at cell C, what we have is AC UC star equals P2 star minus P3 star. If you also underlax this equation with the same factor alpha U, what you get is AC upon alpha U times UC star, right, equals P2 star minus P3 star plus, on the right hand side you have to add this extra term, that is 1 minus alpha U upon alpha U times AC UC star. This also has to be essentially star star, right? Basically I forgot to write it here. This is also star star, indicating that this is the current iteration value that is available, right? That is available. Excuse me, right? Okay, so essentially you would use these two equations in the solution of the star momentum equation. So when you, after you have guessed the pressure and guessed the velocities, you would use this equation to solve for convergence of these values. Okay, to solve using the Gauss Seidel or something. In this particular case you don't have to, because you know all these things on the right hand side, so it can be computed. Okay. Of course, now because we have modified this above equation to use underlaxation, we not only need pressure guess, but we also need the velocity guess in order to calculate the velocity values. Okay. All right. So now the algorithm is actually complete. We have to, of course, write a code for this and run it so that we would obtain the values for UB, UC, and P2. Okay. So that we will do it in the next class. But for today, we will do the remaining two problems as well and formulate them as such. Now, one question you may have is, okay, what about, so instead of using this equation, now what we are saying is that, okay, we will use this equation with underlaxation, but don't we have to go back and redo everything? Because if we have changed the momentum equation, don't I have to go back and do the this correction equations again? Right, for example, now that, so instead of 3 and 4, we are going to use the corresponding underlaxed equations. Then don't I have to redo all these calculations of UB prime and use the correct equations, isn't it? The underlaxed equations or not? So that is the question. The question is, why am I doing 3, 4? Why are we obtaining these from this equation? And then we are saying, okay, we cannot solve this equation. We want to do underlaxation and change these equations to something else, right? Which are the corresponding underlaxed equations. Now the idea is, even if you use the underlaxed equations here, in the simple approximation you will have those terms also will be neglected, just like the sigma A and B U and B prime. The contribution coming from this sigma A and B, sigma A, B, U, B primes also will be neglected. Okay, so essentially they will not be considered. That is the simple approximation. Excuse me. So as a result, it doesn't matter whether you had used the underlaxed equation for deriving the velocity correction, pressure correction equation, or the regular equation. Okay, fine. So that finishes the setting up of the first problem, that is the problem 6.4. Let's move on to the second problem, that is 6.5 from chapter 6 of Vatangkar's book. Okay, so what this is basically, this is again this is a flow through a converging nozzle. Okay, and the flow is going in the positive x direction, so it's going from essentially left to right, So there is a converging nozzle, and then again the values 1, 2, 3 here, locations denote the places where the pressure is stored, and A and B denote the locations where the velocities are stored. Okay. All right. Then two equations are given. The first one is d by dx of rho UA. What is this equation? This is basically your continuity equation, right? And what about this case? This is d by dx of rho UA, U equals minus A dp dx. What is this equation? This is your x momentum equation. Okay. Now what about the terms here? Of course, this is the pressure gradient. And what is this term? This is now the convection term, right? Basically rho UA, this is basically the convection term. Okay, so we have, and we don't have any source term, so source term is 0. Also, the effective areas at these locations are given at A and B. Okay, and the density can be taken to be 1 everywhere. That is what is given. Then, because this is a nozzle, so beyond 1 the area kind of grows very large. As a result, the velocity is quite small here. Okay, and the area is very large and the velocity is very small ahead of upstream of 1. Okay, so the effective areas are given. Area, cross-sectional area at A is 3, cross-sectional area at B is 1, and the pressures are given. Again, this is similar to the previous problem. Both the boundary conditions given are the pressure. P1 is 28 and P3 is 0. That's what is given. And it is also given that fluid upstream of point 1 basically here has negligible momentum, right? That means upstream of 1 has negligible momentum. That means the flow rate upstream of this can be taken to be 0, because if you denote flow rate as rho UA, the momentum is mass times velocity. So mass is your rho A times U, right? So upstream of 1 here, velocity is so small and the cross-section area is so large, and essentially the momentum can be taken to be very small. Okay. All right. This is an approximation that is given. Okay. So this is an approximation that is asked to be made while solving the problem. Okay. Fine. Then what else? Essentially, you are asked to calculate what is the velocities at A locations A and B. That is the A and B is the velocity control volumes, and at the pressure control volume, that is P2. So you have to calculate what is UA, UB and P2. And it is basically given that U's initial guess equals 5/3 for UA, 5 for UB and 2.25 for pressure. Okay, that is basically, when you write the code, you can use this as the initial guess and solve the equations. As of now, we will try to set up the complete algorithm using simple. Okay, so again, what is the first step? First step is to write the momentum equations for the velocity control volumes, that is for A and B. Write the momentum equations, then derive the prime equations, star equations and prime equations for A and B, then write the continuity equation discretization for cell 2 and relate the velocity corrections that you got from A and B in terms of pressure corrections, and substitute for pressure corrections, essentially get a pressure correction equation, right? So that is the idea. So we start off with momentum equation, that is this equation, discretize for A, then discretize for B, followed by discretize this for cell 2. Okay, so for cell A we have 1 and 2 as the faces, for cell B we have 2 and 3 as the faces, and for cell 2, the pressure cell, we have A and B as the faces. That is kind of good to remember. All right, so cell A is basically going from 1 to 2. So what we have is integral 1 to 2 d by dx of rho UA U dx equals integral 1 to 2. On the right hand side we have minus A dp dx. Okay, this being the convection term, we can write this as the flow rate. That's basically rho UA equals F times U. So if you apply Gauss-Diagonal's theorem and so on, what you basically get is you get FE phi east, right? Or you can even integrate it here, because this is 1D, you don't need to invoke Gauss-Diagonal's theorem. So this basically gives you rho UA U, that is F times U. You calculate at both the limits, that is F2U2 minus F1U1, right? And on the right hand side we have minus A, because this is a coefficient, this is taken to be at the cell centroid value. So for cell A, this is basically A sub A, this is minus A sub A times integral dp dx dx would give you integral dp, which will give you pressure. That means if you apply the limits, this is basically P2 minus P1. Okay. Now, of course, because we are given the convection term, okay, we will make an approximation. We will use the upwind difference scheme, although it is not specified in the problem. We will apply upwind difference scheme. We will use upwind difference scheme. Essentially, what that means is that if Fe is greater than or equal to 0, then U little e equals Up, or if Fe is less than 0, then U little e equals U capital E. But fortunately, in this case, you don't have to look for less than 0 cases, because all the flow rates are positive, right? Because the flow is going from in the essentially flow is in the positive x direction. As a result, all f values are greater than or equal to 0. In fact, all are greater than 0 because there is some flow that is happening. Okay, that means f2 is, because f2 is greater than or equal to 0, what will be the value of u2? u2 is basically, if you go here, f2 is positive, so u2 can be taken to be its upstream value, that is ua, right? Similarly, if f1 is positive, what will be the value of here? The value here would be f1 is positive, u1 can be taken up whatever u upstream of 1, right? That means f2 is, because it is positive, u2 can be taken as the upstream value, and u1 can be taken as u upstream of 1, okay? But it is given that the momentum upstream of 1 can be neglected. That means f1 can be taken to be 0. As a result, this term is 0. That means what we are left with is, we are left with f2 ua equals minus aa, or if I absorb the minus inside, we can write this as aa times p1 minus p2, okay? All right. So we have f2 ua equals aa times p1 minus p2. And if you do the same exercise for cell B, what we get is integral 2 to 3, because for cell B we have the phases is 2, 3, right? So that means we can write this as integral 2 to 3 d by dx of rho u a u dx equals 2 to 3 minus a dp dx dx, right? That means again this is f times u, so is the integration value, apply that at both the limits, you get f3 u3 minus f2 u2 equals, cross sectional area for cell B is AB, that is evaluate the cell centroid, times integral dp dx dx would give you dp, so this is basically pressure, integral dp would be pressure, that means p3 minus p2, or if you absorb the minus inside, you get ab times p2 minus p3, okay? That is understood. Now of course you have to apply again upwind difference scheme for the convection terms, right? That means f3, because f2 is positive, so u2 equals ua and u3 equals ub, right? So because f3 is positive, u3 equals ub, u2 equals ua, right? This is the upstream values for these flow rates. All right, that means what we get is for cell B we get f3 can be written, u3 can be written as ub, u2 can be written as ua. Now remember that we are not replacing the f3 with fb here, okay, or f2 with fa. You are only replacing, because upwind difference scheme only tells you to replace phi sub e with the upstream values, not the flow rates, right? So these f's will remain the same. That means f3 ub minus f2 ua equals ab times p2 minus p3, right? Similar to what we had here, but here we didn't have the other term, because the upstream value of the mass flow rate curve was given that you can take it as negligible. Now one question that might pop up in your head is basically, okay, we don't have storage for velocities at the points 2 and 3, what do I do for the flow rates? That is where we are coming down. Essentially we'll go and see if we can do something for these flow rates from the continuity equation. So we are now done with deriving the moment, discretizing the momentum equations for cells A and B, right? Now we look at the continuity equation for cell 2. That means cell 2 has got essentially limits as A and B as its phases. So that means integral A to B d by dx of rho ua dx equals 0, right? This is basically integration would be rho ua applied at B minus A. So basically what we have is rho ua B minus rho ua A equals 0. This is nothing but your flow rate at B minus flow rate at A equals 0. That means FA equals FB. So FA equals FB, what does that mean? That means the flow rate, of course, going through mass flow rate going through here is same as the mass flow rate going through here. In fact, that means that the mass flow rate going through 2 and 3 and 1 should also be the same, because of from the principle of conservation of mass. right? That means not only is your FA equal to FB, you can also take F2 equals FA equals FB equals F1 equals F3, right? Because this is conservation of mass. Or even if you take F2 as linear average of A and B, you will still get both of them equal, being you get a F2 equals FA equals FB, right? Now this is where we can replace the F2, F3 that we have here with either FA or FB, right? So I can now write this as FBUB minus FAUA equals AB times P2 minus P3, right? That can be written. That means our momentum equations, so these are the discrete momentum equations for cells A and P, okay? What we have is FAUA equals AA times P1 minus P2. And for cell B, we have FBUB minus FAUA equals AB times P2 minus P3. Okay. So how do we construct the star equations here? Star equations are basically use a guess value for pressure, then the velocity values would be the star values that these equations have to be converged to, right? That means the star equations for cell A is FAUA star equals AA times P1 star minus P2 star, and FBUB star equals FAUA star plus AB times P2 star minus P3 star. Okay. Alright, that is given. Then how do we construct the prime equations? Prime equations is basically subtract the star equations from the original equation. That means you get FA times UA prime, because UA minus UA star gives you UA prime, equals AA times P1 prime minus P2 prime. Okay, that's the prime equation for cell A. Prime equation for cell B would be FBUB prime equals FAUA prime plus AB times P2 prime minus P3 prime, right? But in this we make because of the simple algorithm, the contribution coming from the sigma A and B prime, that is this term, would be taken to be 0. Okay, so essentially this approximation is coming from simple algorithm, right? This is basically coming from simple algorithm. Okay, that your FAUA prime equals 0. Okay, so basically this is equals 0. And we also know that P1 and P3 are given. P1 is given as 200, P3 is given as 38, I suppose, right? P1 is given as 28 and P3 is given as 0. That means P1, the pressures are given, so the pressure corrections are 0. So P1 prime equals 0 and P3 prime equals 0, right? That means this is 0 and this is 0. And this is taken to be 0 because of the simple approximation, okay? Alright. So this is 0 as such. That means we have these things. Then we can write this as UA prime as AA upon FA, right? This is what we are calling it as some D, right? Remember we had delta Y upon the central coefficient A east, that we are written as D little e. Similarly, we have AA prime equals capital AA by FA times minus P2 prime. So we can write this as minus DA P2 prime, where DA is your AA upon FA, this coefficient. Similarly, UB prime equals AB upon FB, that is AB upon FB times P2 prime. So this can be written as DB P2 prime, where DB equals AB upon FB. Okay, that means we got now velocity corrections for cells A and B in terms of the pressure corrections, that is P2 prime. So this is your velocity corrections in terms of pressure corrections. Now these are important because this is what we need to substitute in the continuity equation. So from the continuity equation, what we have is we have FB minus FA equals 0. So which of course can be decomposed into star and prime values, and if the star values are sent to the right hand side, what we get is we get FB prime minus FA prime equals FA star minus FB star, right? This is basically sent to the right hand side. Then density is given as 1, so we can write FB as rho UB, right? Rho UA, that means rho is 1, so we can write this as UB prime AB minus UA prime AA equals FA star minus FB star, right? So the right hand side, this term is already known. This is the mass imbalance for cell 2, right? The amount by which the velocities do not satisfy the conservation of mass for cell 2 is the FA star minus FB star. Now this is not equal to 0. If this is equal to 0, then we have reached convergence, right? For momentum equations also, right? That's why this is not equal to 0 at the moment. This we could have computed, okay, before coming to this step. Now we substitute for AB prime, UA prime and UB prime from these equations. So substitute for UB prime as dB P2 prime and UA prime as minus dA P2 prime. And then write an equation for P2 prime. So if I substitute that, then what you get is UB prime equals dB P2 prime. So this is basically dB AB, and you have, this is basically minus dA P2 prime, that becomes a plus dAAA times P2 prime, right? That is P2 prime equals, on the right hand side we have FA star is rho equals 1. So this is UA star AA minus UB star AB, right? Because we only know the star values and the cross-sectional areas. That means we know everything on the right hand side. We know the coefficients here, the cross-sectional areas are known, and the D values are known. That means we can write an equation for pressure correction for cell 2. So this is basically the pressure correction equation for cell 2. Again, we have only one cell, so we don't need to solve for Gauss-Seidel. Rather, using the starred values for velocities, right, we can calculate P2 prime. Okay, that can be calculated. Okay, fine. So this is the pressure correction equation. Now once you obtain the pressure correction, you can now correct the velocities using UA equals UA star plus UA prime. UA prime equals minus dA P2 prime. So this is UA star minus dA P2 prime. Similarly, UB equals UB star plus UB prime. That means UB star plus UB prime is your dB times P2 prime. And P2 equals P2 star plus, again I use some under relaxation because of the non-linearity of the convection term this time, right? This is basically P2 star plus alpha P times P2 prime. So owing to the non-linear convection term, we need to also under relax the momentum equations and under relax the pressure while we are correcting it. So now how do we under relax the momentum equations? The original momentum equation, the star equation, is FA UA star equals AA times P1 star minus P2 star. So if you are to under relax, then you divide this by alpha and add an extra term on the right hand side. This becomes FA by alpha U times UA star equals AA times P1 star minus P2 star, plus you get 1 minus alpha by alpha times this quantity, that is FA UA star star. Okay, basically indicating that these terms are already known. Okay, so that is your under relaxed momentum equation for cell A, okay, which we will use when you solve for the guess velocities and guess pressures to calculate the converged velocities at the cells. Okay, this is what you will use. Again, the momentum equation for cell B was given as FBUB star equals FA UA star plus AB times P2 minus P3 star, right? Remember, this is what the original equations we had written, right? So we had these two equations, right? And we wrote the star equations here. Now we are trying to under relax them, and if you are to under relax the cell B, then what you get is basically this is FP UB star, so you'll get 1 by alpha U FP UB star equals FA UA star plus AB times P2 star minus P3 star, plus you get 1 minus alpha U by alpha U FB UB star star. Okay, so this is basically your under relaxed equation for cell B. Fine. So again, because of the non-linearity of the convection term, we have to do multiple iterations here so that we converge to a final solution that is driven through continuity satisfying velocity fields, okay, by the simple algorithm. All right, let's look at the final problem from the book, that is basically problem 6.7, which is a pipe network that is, let's say, distributes water to a residential area. Okay, essentially we have different locations here, and the flow through the pipe, the flow rate Q is given as some hydraulic conductance C times the delta P, where delta P is the pressure drop over the length of the pipe. Okay, This is basically the P upstream minus P downstream, that is the pressure drop over the length L, and C is the hydraulic conductance and Q is the flow rate. Okay, and the pipe network is shown here. So the locations, dark circles here, 1, 2, 3 all the way to 7 are the locations where the pressure is stored, and the arrows here denote the direction of the flow. Okay, and they are also the locations where the velocities are stored. So for example, the velocity is stored as at A, B, all the way to F. Okay, now a few pressure values are given, that is P1, P2, P4, P5 is given. So all these things are given. 3, 6 and 7 are not given, and the flow rate also through F is given. So QF is given, this is 40, and the hydraulic conductivity is given for all of them, that is CA is given as 0.4, CBDF, that is BDF, all these three are 0.2, CC and CE are given as 0.1. Okay, all the hydraulic conductance given. So we were asked to calculate what is the pressure P3, P6, and what is the value for QA, QB, QC, QD and QE. You need to calculate what is A, B, C, D and E. Okay, these flow rates is what you need to calculate, and the given equation is only the Q equals C times delta P. Now what equation is this? This is momentum equation, or this is now what kind of an equation is this thing? What do we take this as? We should take this as basically momentum equation, isn't it? Because you have kind of an integrated momentum equation, okay, where the flow rate equals C times delta P. Okay, so dP dx is not given. Similarly, the dP dx of this guy is not given. Okay, so this is the momentum equation. That means we have to solve for this equation at locations A, B, C all the way to F, right? That's what we have to do. All right, so we have to calculate these two pressures and the flow rates for A to E. All right, that means we know that this is momentum equation. So if you were to write for cell A, the limits are 1 and 3. So you have to integrate 1 to 3 Q dx equals 1 to 3 C delta P dx, right? Now what is Q? Q is the flow rate. Under what term do you want to call this as? What type of term is this? This is basically like a source term, right? Because Q is kind of constant for the entire cell, and the cell centroid value is what you want to take it as a representative, right? So Q would be QA and will be constant, so integral dx will be delta x, so this will be delta x equals C. Again evaluate the cell centroid, that is CA. What about delta P? Delta P is also now constant, so CA delta P times integral dx would be delta x, right? Basically x3 minus x1, x3 minus x1. So these two delta x get cancelled. So what you get is QA equals CA times delta P. And what is delta P? Delta P is the pressure drop across the length, and the length is for 1, 2, 3, right? So along this much length, right? That means P1 minus P3 would be delta P for length A, right? For the vector A. So that means this is basically QA equals CA times P1 minus P3. Similarly, you can write the equations. So what will be QB? QB would be equal to CB times P3 minus P2, right? Because the flow is going that way. Similarly, what would be QC? QC would be equal to CC times P4 minus P3. So that is QC equals CC times P4 minus P3. And what would be QD? QD would be CD times P3 minus P6. So that is your QD, right? QD equals CD times P3 minus P6. And QE would be CE times P5 minus P6. So that is QE is CE times P5 minus P6. And similarly, you can write what is QF equals CF times P6 minus P7. So these are the discrete momentum equations for cells A through F, right? Okay. Now once you know these, basically these are the starred equations, right? These are the starred equations. If you were to put star here for P1 star and P3 star, and then what I obtain here is your QA star, right? This is your QA star. Now if you subtract off the starred equations from the non-starred equations, what you get is the prime equation. So we can write the prime equations on the right hand side. Those are nothing but QA prime equals CA times P1 prime minus P3 prime. So it is kind of easy to see from these equations how to write them. And QB prime equals CB times P3 prime minus P2 prime. Similarly, QC prime equals CC times P4 prime minus P3 prime, and QD prime equals CD times P3 prime minus P6 prime, and QE prime equals CE times P5 prime minus P6 prime, and QF prime equals CF times P6 prime minus P7 prime. Okay, so we got all the pressure correction, essentially prime equations in terms of, we don't have velocities now, but we have flow rates, right? Essentially Q is like our velocity. So we kind of related the velocity corrections or flow rate corrections in terms of pressure corrections. Alright, so now what is the step that follows? Basically you have to look for the continuity equation, but we were not given continuity equation, right? Because the only equation we are given is Q equals C times delta P. But what are the locations where do we have to apply continuity equations? We have to apply continuity equation at the pressure cells or the primary cells. That means we will apply this at 1, 2, 4, 3, 6, 5, 7, right? But again, we don't have to apply at 1, 2, 4, 5 because 1, 2, 4, 5 the values are already given. So we need to apply only at 3 and 6, right? And at 7. So, but at 7 we don't have to apply because the flow rate is already given. So that is flowing in. So we need to apply continuity equation at 3 and 6. What would be the continuity equation at 3? I mean, continuity equation is basically at 3 is whatever that is flowing in minus whatever that is flowing out should be equal to 0. That means for cell 3, the conservation of mass is QA plus QC minus QB minus QD equal to 0. That is conservation of mass for cell 3. That is QA plus QC minus QB minus QD equal to 0. And the continuity equation for 6 would be QD plus QE minus QF equal to 0, right? So those are the continuity equations. Now that means we can write the continuity equations for pressure cells. That is for cell 3 is QA plus QC minus QB minus QD equal to 0. Now this can be decomposed into star and prime quantities, and the star values can be sent to the right hand side. So what you get is QB star plus QD star minus QA star minus QC star on the right hand side, which is basically known, right, from the converged star values. And on the left hand side we are left with QA prime plus QC prime minus QB prime minus QD prime, right? Alright, so we are left with this. Now we can substitute for QA prime, QC prime, QB prime and QD prime from the equations we have derived here, right? So we will substitute for them. That means we substitute QA prime equals CA times P1 prime minus P3 prime, QC prime as CC times P4 prime minus P3 prime, minus QB prime as CB times P3 prime minus P2 prime, and QD prime as CD times P3 prime minus P6 prime equals everything on the right hand side. Now we also realize that because the pressure values are given at locations 1, 2, 4 and 5, the P primes at these locations are 0, right? We don't need to do any pressure correction there, so the pressure correction is 0. So as a result, P1 prime is 0, P4 prime is also 0, P2 prime is also 0, and these two are not 0. Okay, that means we can collect P3 prime terms. So P3 prime equals minus CA minus CB minus CC and minus CD. That's what we get. And we have plus P6 prime that is coming from here, which is P6 prime times CD equals something on the right hand side, that is basically QB star plus QD star minus QA star minus QC star. Okay, so this is now your pressure correction equation, right? This is very different from what we had till now. Till now we had only one pressure cell. Now we have two pressure cells, that is C3 and 6. So this is pressure correction equation for cell 3 that also contains contribution from cell 6, right? That is P6 prime is also there. Okay, so we have two unknowns here, but this is one of the equations. The other equation will come from cell 6. So for cell 6 what we have is we have QD plus QE minus QF equal to 0. That is the continuity equation for cell 6, QD plus QE minus QF equal to 0. Right, so if you are to again write that equation, then we have decompose this into star and primes. The equation we get is QD prime plus QE prime minus QF prime equal to QF prime star minus QD star, sorry, QF star minus QD star minus QE star. So the right hand side thing here is already known, and because QF prime is basically given, QF is given as 40, QF prime would be equal to 0, right? Because this is given, this is equal to 0, and we can substitute for QD prime in terms of pressure corrections, that is CD times P3 prime minus P6 prime plus CE times P5 prime minus P6 prime minus this is 0 equals QF star is nothing but QF, right? So this is QF minus QD star minus QE star, which is already known. And P5 is given, so as a result P5's prime is, this is 0, okay? So this is 0. That means we again have equation in terms of P3 prime and P6 prime. So P3 prime times CD plus P6 prime times minus CD minus CE equals QF minus QD star minus QE star, okay? So this is our other pressure correction equation for P3 prime and P6 prime. So we have, this is the second equation, and the unknowns are P3 prime and P6 prime. So we have two equations and two unknowns. Of course, in a traditional sense, we would have solved for Gauss-Seidel here, right, for solving the pressure correction equation. But here we have two equations and two unknowns, right? So we don't have to solve for Gauss-Seidel. We can directly solve for two equations, two unknowns. So solve for P3 prime and P6 prime. Okay. Then once you know the pressure corrections, you can update the pressures using P3 equals P3 star plus P3 prime, and P6 equals P6 star plus P6 prime, and then we correct the flow rates, right? Essentially QA equals QA star plus QA prime, where QA prime equals minus CA times P3 prime, because the other contribution of P1 prime is 0. Similarly, QB equals QB star plus CB times P3 prime, QC equals QC star minus CC times P3 prime, and QD equals QD star plus CD times P3 prime minus P6 prime, and finally QE equals QE star plus QE prime, for which we can write minus CE times P6 prime. These are basically the same equations we have derived before. Only thing is that we have now set these underlying quantities to 0, because those corrections are all 0, because the boundary conditions for pressure are given. Now what do you see? You got you corrected your flow rates using the flow rate corrections. Now what about how many times? So do we need to iterate here? Do we need to iterate? Because at this point our solution satisfies, the flow rates are satisfied, but what about the momentum equation? Is the momentum equation linear or not linear? Momentum equation is linear. That means we don't have to iterate, because whatever in one iteration it will basically converge, right? Because the momentum equation is linear, right? The pressure corrections only will affect the flow rate. So because this is linear, we don't need to iterate, right? It will just converge in one iteration. Okay, so that we will see when we try to solve these problems using a code. Okay, so okay, so basically that is all for today. So in the next lecture we will look at the corresponding programs. Okay, and we will try to run the programs for these three problems. So it will be good if you can keep these notes handy, okay, so that we can refer to these equations and then look at the program, try to run the program and see and obtain the results for each of these problems. Okay, all right, so I'm going to stop here. If you have any questions, send them to me through email. Okay, all right, thank you. Talk to you in the next lecture.